Let's see how network layer information can be seen and analyzed in a Wireshark packet capture. I have a screenshot from a Wireshark packet capture, and you can see that the second packet that's been captured has been highlighted, and then in the packet details window, the network layer information has been expanded to show us all of the things happening at the network layer. So let's see what's happening in this particular packet that we're examining. We can see that, first of all, the network layer protocol or internet layer protocol that we were dealing with was Internet Protocol version 4, IPv4. We can also see that the source IP address was 192.168.1.109. You can see it also highlighted up here in the packet list window area, and that the destination IP address was 192.168.1.1, and we can also see that up here. We can see that at the higher layer, this is a TCP protocol packet, but if we limit ourselves to just the IPv4 fields or the IPv4 information, we can see the different types of control information that's contained in every IPv4 packet. For instance, the version number, which is 4, identifying this as an IPv4 as opposed to IPv6 packet. The header length, or the length of the header, this is the minimum size of an IPv4 header. The differentiated services field, which is used for packet prioritization and is useful for applications like voice over IP. The total length of the packet. The identification number, which is used for fragmentation. The flags, you can see that the DF bit has been set, which stands for don't fragment. This packet is not large enough or is not identified for fragmentation. Fragment offset. The TTL, or time to live, which is set to 128. Every time a packet is routed from one hop to the next, the TTL number is reduced. When the TTL number reaches 0, the packet is dropped, ensuring that packets don't circulate on the internet forever on an endless loop. The TTL value is also used in ICMP trace routes and pings. The protocol field lets us know the type of information to expect in the data portion of the packet. A 6 identifies the data portion of this packet as being a TCP packet. The header checksum field, which allows routers to check to see if there are any errors or inconsistency in the IP header. If there is, the packet will be dropped. And then lastly, the source and destination IP addresses, which are the most important part of the IPv4 packet. Let's take a look at 2 more screenshots of Wireshark packet captures, and we'll see some similarities and differences. The next screenshot shows us that now we're looking at the 8th packet captured. The packet's source IP address is also 192.168.1.109, and the destination IP address is 192.168.1.1. Except this packet is an HTTP GET request. So this is a request to a web server located at 192.168.1.1. You can see that the network layer or internet layer information has been expanded, that it's also the IP version 4 protocol, and that we have similar information in the different fields. Notice under the total length field that this packet is 411 bytes compared to the previous packet, which was only 52 bytes. You can tell that this packet has a lot more information, or is a much larger packet than the previous one. If we look below the Internet Protocol version 4 information, we can see the TCP information, and then below that there's Hypertext Transfer Protocol or HTTP protocol information in this packet as well. I'll move forward to the next packet, and you can see that this packet is the 16th packet captured right up here. It's also from host 192.168.1.109 to host 192.168.1.1, except this is the ICMP protocol. You can see from the information in the packet list window that this is an echo or ping request. If we look in the Internet Protocol version 4 information in the details area, we can see some minor differences. The version is still 4, the header length is still 20 bytes, but we can see that the flags are slightly different, and that the protocol field is now set to 1, indicating that the data portion of this packet is an ICMP protocol message. Notice that in the details window at the bottom here is an expanded area to look at the header information specific to ICMP. This screenshot shows a packet capture using Wireshark and the network layer information from an IPv6 conversation. Let's take a look at it. In this screenshot, we can see that the highlighted packet is packet number 46, and that the source address up here in the packet list window shows that it is a global unicast IPv6 address. You can see this starting with the 2001:6F8. The destination address is also a global unicast address, 2001:6F8-900, and so on. And if we look over in the protocol field, we see that at the upper layers, this is a TCP packet, and that it's an attempt to establish an initial communication with an HTTP web server. If we look down in the network layer information area, you can see that the IPv6 information has been expanded. Let's take a look at some of the protocol field information for Internet Protocol version 6. First of all, you can see that the amount of information in the IPv6 header is much smaller than in the IPv4 header. Now, there are some interesting features. For one, you can see that the version field is the same. In this case, it says 6, identifying this packet as IPv6. We can also see the binary 6 here. The next field is the traffic class field. The traffic class field serves the same function as the differentiated services field in an IPv4 packet. It handles traffic prioritization and congestion. The next section you can see is the flow label. The flow label field is a new field for the IPv6 protocol. Its purpose is to maintain the same packet flows through routers and switches so as to help real-time applications that need packets to arrive in the same order. You can see the next field is the payload length field. This is the same as the total length field in the IPv4 header. This field tells us the total size of the packet, in this case 40 bytes. The next header field serves the same purpose as the protocol field for IPv4. You can see that it's identifying that the upper layer data portion of this packet is a 6 or TCP. The hop limit serves the same function as the TTL field in an IPv4 packet. You can see that the hop limit currently is set to 64 hops. Once this decrements to 0, the packet will be dropped. Next, we have the source IPv6 address, the destination IPv6 address, and then at the upper layer, we can see that this is a TCP packet with TCP header information. Let's take a look at the next screenshot. In the next screenshot, you can see that we've now highlighted packet number 49, and now we have a connection with this web server. This packet is now a GET request to the web server. If we look down in the expanded Internet Protocol version 6 packet details window, we can see that the payload length is a lot larger. We can see below the IPv6 information, the TCP information, and that now there is HTTP protocol information as well within our GET request. This is our GET request to get a web page. If I go to the next screenshot, the last screenshot shows an ICMP version 6 neighbor solicitation message. If we look up in the window at the highlighted packet here in packet number 1, we'll see that the source address this time is not a global unicast IPv6 address, but a link local address. We can tell that from the FE80 here. We can also see that this link local address used EUI64 to resolve the interface identification portion of the address. We can tell that by the FFFE within the address. The destination address is an FF02 IPv6 address, indicating that this is a multicast packet. If we look over at the protocol, we see that it's ICMP version 6, and then information about the packet tells us that this is a neighbor solicitation message for the same device that we were contacting in the earlier screenshots. The function of this packet essentially is similar to an ARP request in IPv4. We need to discover the link local address of this device, so we send out an ICMP version 6 neighbor solicitation message, multicasted, and we're hoping to get back a link local address from this neighbor. If we look down in the expanded details window, we can see the version is 6, traffic class flow label, payload length, which is the entire length of the packet, the next header field, which is like the protocol field in IPv4, indicating a 58 that this is an ICMP version 6 message in the data portion of the packet. The hop limit, 255 hops. This is similar to the TTL field. And then the source, link local address, and the destination multicast IPv6 address. At the bottom, below the IPv6 information, we can see that there's an expandable area specific to the Internet Control Message Protocol version 6. Let's use Packet Tracer to learn about routing tables. We've learned about two types of routing tables, a host routing table on a PC versus a router's routing table. Let's take a look at both. If I click on PC1 and I click on the desktop tab and the command prompt, I can put in the command netstat --r to look at my routing table. Now this PC host routing table is a very simplified version of a routing table, and in reality, if it was a real PC, there would be many more entries. We can see that under active routes, there is one active route, and this is the default route. Our default gateway is located at 192.168.10.1. So there's one route, the default route. We can also see that there are different columns of information: the network destination, the net mask, the gateway, the interface, and the metric. We can see that we have a 000 or all networks destination using a 000 or all networks net mask, and the gateway address of 192.168.10.1. This is the local router. The exit interface, which we will use to get to this gateway, will be our own 192.168.10.3 interface. The network distance for all networks to the gateway is a metric of 1. If this was a real PC, we would also see many more entries like the 192.168.10 network. We would see a limited broadcast entry of 255.255.255.255. We would see a directed broadcast entry for 192.168.10.255, multicast address entries, including possibly IPv6. Now let's take a look at the router's routing table. To look at the router's routing table, I'll click on router R1, click on the CLI tab to get to the command line interface. I'll press enter to get to the command line. I'll type enable to get to privileged exec mode, and then the command to see the routing table is show IP route. I'll press the spacebar to get the rest of the output. Now the routing table tells us all of our network routes. If we scroll to the top, you can see that there are codes, letter codes, that allow us to know what the beginning of every line entry means. If we scroll down to the bottom, we can look at the routing entries. The router's routing table is similar to a host PC's routing table, except there are no columns to separate the information. The routing table has information about connected routes, remote network routes, and default routes. All three can be seen here in this routing table. For instance, if we look at these two entries here, these are remote network routes. If we look at these entries here, these are for connected network routes. The last entry in the routing table is a default route, or gateway of last resort. Notice the quad 0 all networks address with all zeros net mask. If we look at the codes at the top, we can see that the D stands for EIGRP, making this our two remote networks. We can see that the letter C stands for connected, showing us that these entries starting with C are our connected network routes. The capital L stands for the link local address. Notice 192.168.10.1, as opposed to the connected network 192.168.10.0. This is the local interface address, connected to gigabit 0/0. If we want to understand the information based on the destination networks, then we can see that the destination networks are the first part of the entry here. This is the 10.1.1.0 destination network, the 10.1.2.0 destination network, the 192.168.10.0 destination network, and so on and so forth. The metric information is contained within the brackets. This is the administrative distance, and this is the metric. The gateway, or what we would call next hop address, is located here. The time since we've last learned about this route is located here, and the exit interface is located here. These are just some of the basics of a router IPv4 routing table. Let's take a more in-depth look at the router's routing table. But before we do that, let's discuss a few items. First of all, the routing table that we're looking at is the R1 router's routing table. The router has 3 connected networks. A connected network coming off of its interface here, a connected network coming off of its interface here, and a connected network that goes from here on this serial interface over to router R2. If I was to highlight the 3 connected networks, they would look like this. Here's one connected network. Here's another connected network. And here's the third connected network. So these 3 interfaces each have a network coming off of them, and these are the 3 connected networks on router R1. The 192.168.10 network, the 192.168.11 network, and the 209.165.200.224 network between R1 and R2. R1 also knows about 2 remote networks. The 2 remote networks R1 learned about from router R2. The 2 remote networks are the 10.1.1.0 network and the 10.1.2.0 network. For R1, the next hop router is R2, located at 209.165.200.226. Let's look at the R1 routing table closer now that we know about these connected networks and these remote networks. I'll put in the command show IP route to examine the routing table. Looking at the routing table, we can examine the first 2 routing entries here. We can see that both of these entries are for the remote networks 10.1.1.0 and 10.1.2.0. These are the networks here that are not connected to router R1. R1 learned about these remote networks from router R2 using the EIGRP dynamic routing protocol. We can see that here by the D at the beginning, which stands for EIGRP, or the dual algorithm that's used by EIGRP. Now, if we examine these two routing entries, we see the destination network, the subnet mask, and then this number is the administrative distance or the trustworthiness of the route, and this is the metric or rating of the route. Then we can see that to reach the 10.1.1.0 network, we need to go through the next hop router via IP address 209.165.200.226. This is that next hop address. In other words, if we want to get to this network up here, we need to go through router R2, whose IP address is 209.165.200.226. We can also see the timestamp that tells us how much time has expired since we last learned about this route. The last piece of information is the exit interface. So, to reach the 10.1.1.0 network, we need to go to the next hop router at 209.165.200.226, and we need to exit our own serial 0/0/0 interface. That's this interface here on router R1. Notice that if we examine a connected network routing entry, in this case the 192.168.10.0 network, there is no next hop router IP address because it's a directly connected route exiting out of the gigabit Ethernet 0/0 interface. Notice that the 192.168.11.0 network, which is also a connected route, exits the gigabit 0/1 interface. Your routing table tells you all of the currently available networks that you can reach. It's very important to be able to read and understand your routing table. Let's walk through the router boot up process. As you can see, I have a console connection using TerraTerm to a Cisco router. There are three major phases. In the first phase, the router runs the power on self-test or POST program. Located in read-only memory or ROM, the power on self-test checks for errors in the hardware like the CPU, the DRAM, and also the NVRAM. After the system posts, the router then runs the bootstrap program. The bootstrap program is also located in ROM. This is the end of the first phase. The purpose of the bootstrap program is to locate and load the Cisco iOS software. The iOS is Cisco's operating system for the router. The Cisco iOS is located by default in flash memory. If the iOS image file is not found in flash memory and then loaded into RAM, then the router will look to a TFTP server on the network to see if it can find another iOS image. After the iOS is completely loaded, the router then loads the configuration file, known as the startup config file. This file contains all of the configured settings for the router, such as the host name and interface IP addresses. The configuration file is located in non-volatile RAM, or NVRAM, in the router. If the router cannot find the startup configuration file in NVRAM memory, it will also look to a TFTP server on the network to see if it can find a configuration file. If a configuration file is not located on a TFTP server either, then the router will enter setup mode, which is a configuration wizard meant for initial setup. Let's watch the process in action. I'll go back to my TerraTerm console connection and press return. You can see that I now have a console connection to the router. I'll type enable to get to privileged user mode and then type reload. This will reboot the router and we can watch the boot up process in action. I'll hit enter and proceed with reload. I'll hit enter to confirm. Alright, and you can see the system has found the bootstrap. The system has rebooted System Bootstrap version 15. You can see it right there. So the system has performed the post already and now found the bootstrap. It's located the memory. You can see there's 512 megabytes of memory on board. There's a DIMM slot that doesn't have any expanded memory in it. You can see that the system has found the ROM-on or ROM monitor mode, a recovery subset iOS that's located in ROM memory in the event that an iOS is not found. You can see that the bootstrap program has now found the iOS image file and is decompressing the iOS image. You can tell this from the presence of the hash characters. It's finishing the boot up process. It now recognizes that we are running the Cisco iOS software version 15.2, sub-release 3. At the bottom here you can see that the memory, the flash memory on the router has been recognized, and now the configuration is being loaded. Now with this router I've configured one interface, and that is the gigabit 00 interface. So if we look here, I'll scroll up slightly, you can see that the interface gigabit Ethernet 00 has changed its state to up. That's because I've configured it. So we know at this point that the configuration has been loaded, and that's what we see from the output from the router here. At the end now, the router is finished booting and I can press enter. I'm met with the command prompt. I have a console connection to a Cisco 1941 router, and I'm using the Terraterm terminal emulation program to get to the console command line interface. Let's go into the router and issue a show version command to see information about this particular router. I'll press enter to get to the command prompt, type enable to get to privileged exec mode, and then issue the show version command. At the top of the show version command, I can see the iOS software version that we're running. I can see that it's the C1900 Universal K9 version 15.4.3 extended maintenance rebuild version 2. I can also see that the system bootstrap software is version 15.0 and is located in ROM memory. I can also see that this router has only been up for 33 minutes. Not only do I know the version of the Cisco iOS, I also know where the iOS file is located. It's located here. System image file is in flash memory, and the file name is C1900. This is our hardware platform since it's a 1941 router. It's the Universal K9 distribution. It runs in memory. It's compressed, it's digitally signed by Cisco, and this is the version, 15.4, minor rebuild version 3, extended maintenance release rebuild 2, and it's a .bin file. This whole file name is the Cisco iOS image file. If I press the spacebar, we can see the next part of the show version command. We can see that there are 2 gigabit Ethernet interfaces on this router, 2 serial interfaces. We can see that the dynamic RAM configuration is 64 bits wide. There's 255 kilobytes of NVRAM to store our configuration files. There's 250 megabytes of compact flash memory to store our iOS image files. I'll press the spacebar again to get to the next part of the output. Here's our licensing information. The license UDI, or Unique Device Identifier, is made up of the product ID here, followed by the serial number here. We can see the technology package that this router is using. Currently, the technology package that it's using is the IP base and security. We can see that right here since it's the current technology package. Notice that the data package and the NTWK ESS are set to none. The licensing for both of these packages is a permanent license and an evaluation right to use license. On next reboot, we'll have access to both packages. The security package gives us access to advanced cryptographic features like IPsec and intrusion prevention system technology. The last line is the configuration register. Currently, you can see that it's written in hexadecimal format, and it's set to 2102, which is the default. This lets us know that currently, when the router boots, it looks to flash memory for the iOS image file, and then it attempts to load the configuration file from NVRAM. If you were to forget your password to your router, you could recover your router by altering the configuration register so the configuration file wouldn't load from NVRAM on boot up. You can see that the show version command gives us basic information about the router, the iOS operating system running on the router, how long the router's been up. It also tells us the last reload type. You can see the last reload was a normal reload, and the reason for the last reload was that I issued the reload command. You can use this to find out why the system has started and stopped or restarted, and this can be useful in troubleshooting scenarios.